created what I believe is a consistent definition of set, subset, and empty set. And I've done it because I had trouble with the standard definitions, such as 3 shoes on the table. A collection of 3 shoes on the table is a set. Well, if I take the 3 shoes and distribute them around the world, are they still a set? If I remove the 3 shoes, what am I left with? Do I still have a set somewhere in imagination? So my definition of set, which is the concept of container, is not new, but I'm trying to use it consistently. A set is a virtual container with specified content. And a set is created by declaration and content, a set of. For example, if I have 3 shoes on the table, if I refer to a set of 3 shoes, basically what I do is I create a virtual container and put the 3 shoes in that container. Other examples of sets are a set of even numbers, hats, fruit, and so on. Then the empty set is a set with no contents. I'm specifying that there are no contents. Again, virtual container with specified content. What am I specifying about the content? That there isn't any. So in that sense, the virtual container, all I'm left with, if I don't have contents, is the virtual container. So the empty set is the virtual container, and it's designated as, some of the designations are E, phi, and empty brackets. Another example of set is A union B, which is the virtual container with the contents of A and B. Then the subset A, subset of B, is defined by A is a subset of B if every member of A is a member of B. And that assumes there's an implicit assumption there, which not everybody might be willing to accept, that member and test exist, that you have members of A and some way to test whether they belong to B. If you discard that assumption, just leave the original definition up to there, then you come up with the following possibilities. E is a subset of A, and the proof is that it's true for every member of E, or equivalently, it's not true for no member of E. By the same token, E is not a subset of A. The proof is exactly the same as this. It's true for every member of E, and it's not true for no member of E. So if you decide that you're going to take E is a subset of A, you're basically taking it as an axiom, an unprovable axiom. You're saying, I'm going to assume that E is a subset of A. Now, that's okay, you can do that, but if you do that, you have to discard the language of common perception. You're saying E is a subset of A, you're saying that E, which nothing belongs to, nothing is something, which is okay. That's an abstract math, common perception. You can do away, you can disavow common perception for the sake of the mathematical argument. The only condition is that the conclusion that you draw can't then be interpreted in terms of the perception of common language. That's the catch. You can discard the perceptions of common language in your axioms or in your given if you discard the perception, but then you have to discard the perceptions of common language in your proof. For example, using E as a subset of A to prove Cantor's theorem is like saying nothing is something implies endless is not endless. So you can say this at the beginning, say that, I can my language doesn't have to be perceived by common interpretation, but then the result can't be perceived by common interpretation. That's my discussion and definition of set, subset, empty set. Thank you.